Go ahead, Isabel.
Okay.
Excellent.
Yes. Okay. Thank you. So today I'll be discussing my project, which is image-based mechanical modeling of brain tumors. Specifically, it's going to be glioblastomas, and they are a type of an aggressive tumor type which originate in the astrocytes or a glial cell found in the brain. And in the US alone, they account for about 50% of all brain tumors. And unfortunately, the average survival rate is less than a year, and the 5-year survival rate is less than 6%. So there's definitely a need for improved outcomes and quality of life for these patients. And on the left here, I just have some examples of gliomas. So on the top is in the rat brain, which is the kind of data I use, and in the bottom is in the human brain.
You can use the mouse, the cursor to show people.
Okay, so you
Yeah,
can
we will
see
be
it
able to.
now.
Yeah, very well.
Okay,
Good.
okay, perfect. Okay, so some of the available treatments right now include surgical removal, chemotherapy, radiation, or gene therapy. However, as I previously mentioned, these therapies have really poor long-term outcomes, and even more so for those who suffer from recurrence or the return of these tumors. So possibly one of these reasons includes the fact that the tumors are highly variable genetically and molecularly speaking, meaning that one single medicine won't effectively remove the cancer between patients. And even if the patient themselves has multiple tumors, current treatments can't always effectively remove all of them. So some other things I'd like to review is tumor physiology. So just starting from formation, they first start to form, proliferate, and then survive. And in order to receive the nutrients that they require, they begin to form or recruit existing blood vessels via 3 methods, which can include angiogenesis, vasculogenesis, or vascular co-option. And then the mass continues to grow. Sorry, excuse me, to grow and then possibly migrate and invade other structures of the brain. And so the breakdown of the blood-brain barrier is a key feature here. So healthy brain tissue has a very selective semi-permeable membrane that restricts the transport of many molecules into the brain, but the vessels in these cancer tissues are very imperfect and they often have holes in them, which causes fluid to leak from the vessels. And that fluid leakage, along with tumor growth, can lead to great changes in the mechanical environment of the tumor and the surrounding brain tissue. So in my lab, our approach is to embrace the unique environment created by the tumors and make unique mechanical models for each patient or test animal. So specifically, we utilize dynamic contrast enhanced MRI along with pharmacokinetic experimental data to predict 3D mechanical fields in and around the tumor tissues. And in general, the model framework is as follows. We have several experimental data sets along with literature values as input. Then we do some pre-processing of the data on ITK-SNAP, ImageJ, and MATLAB before we feed this into FEBio, which is a finite element solver specifically made to analyze biological systems. And then we take that numerical output and create beautiful contour maps of the data to show that in a visual sense. Okay, so now I'm going to review some of the main ideas of the theory going into the actual computational modeling. So first is the idea of porous media. So porous media is one that's composed of both a solid and fluid phase right here, where the fluid space or the pore space is fully interconnected. So this blue region and, sorry, so with respect to my model, the solid phase is defined as the extracellular matrix, the cells, and the vessels, and the fluid phase is the interstitial fluid, which is the free fluid in between the solid structures of the body. And further, the model that we use is a continuum mechanics model, which means that the tissue is modeled as a continuous material rather than individual particles. So in other words, we don't necessarily model individual cells or vessels at that kind of time or length scale. We model as more generic sense. Okay, and now I'm going to talk about the law which governs the fluid phase, which is Darcy's law. And this law says that the flow is proportional to the difference in pressure and the degree of porosity between 2 points. So on the right is just a diagram here that shows this. In actually geology, this porous media is often used to model soils. So it's one of the easier examples to show. But if we think about the spheres of the soil and so we see that the water flow is proportional to the pressure difference between H1 and H2, and that defines the outflow rates or Q. And then the hydraulic conductivity, which is that funny looking K there defines the general porosity of the tissue. And specifically in the brain, we say that the brain is 20% interstitial fluid, so about 20% pore space. And then 80% would be the solid matrix. Okay, and now I'm going to discuss the theory for the solid phase. So there's three main governing equations. So first is the conservation of mass, and then the conservation of momentum, and then a nonlinear stress equation that we use to model soft tissues. And that's a point I want to make, is that the brain and tumors alike are both soft tissues. So their elastic modulus is around 5 kilopascals. And just for reference, the elastic modulus for aluminum, for example, is around 70 gigapascals. So they're really, really soft relative to other materials that we commonly study in our classes, specifically in mechanics classes. So that conservation of mass equation on the right here, the first one, it shows that at every point we have a source Q, which I'll describe in the next slide. And then in the oops, I went too fast. Okay. And the second equation there is the conservation of momentum, which shows that we must have a balance between the solid state stress and the pressure coming from the fluid phase, which is PI. And then we have
second equation is the force equilibrium, right? Not the momentum equilibrium.
Oops, sorry. Yeah, that might have been a typo on my end.
Yeah, okay.
Okay, thank you. Yeah.
What is the V here? What is the first equation? What is the V? Vs, what is the V?
Yeah, so that's the superficial velocity and then Darcy velocity.
Okay.
So, yeah, sorry, there's a lot of different letters and I didn't want to have a whole long list of all the all the meanings because it would have taken up the whole slide.
Okay. And then what's the number 3 equation?
So number 3 is a Neo-Hookean hyperelastic constitutive equation, which describes the stress-strain relationship. So on the left-hand side, we have the solid stress, and then on the right is again, a nonlinear relationship between J, which is the Jacobian of the deformation gradient F, and then B is the Cauchy stress. And then the gamma and mu are some of the, yes. And then there's some Lame parameters there, which are just some other moduluses, values of the tissues.
Okay, good. Yeah,
okay.
Everybody please ask questions.
Yes, please.
Please list those equations nicely. Those are very important governing equations for the solid and fluid mechanics. So it's actually very useful. Yeah, everybody please ask. Yeah.
Yeah, if I don't explain anything very well, please interrupt me. It's totally fine. And so using these models, we can then account for tumor growth. So we use something called the pre-strain module, and that's available in FE Bio. But in general, it's described in the right-hand side. That's this diagram here. So first we have, oh man, I keep changing, sorry. Okay, so we have some initial tumor size, which we remove from this fake region, and then we let it grow to about 120% of its original size, and then we compress it back down to fit into the original state. And at that point, the tumor now has a pre-strain or a strain, internal strain embedded into its tumor or into the tissue itself. And then that will be the input to our finite element solver so that there's actually a force that is allowing the tumor to grow in the model. Hopefully that makes sense. Okay. Perfect. Okay.
Very nice.
Yes. Thank you. Okay. And the last thing to note here is something called vessel hydraulic conductivity. So basically it states that fluid production, or that source term I mentioned earlier, is proportional to the change in pressure in the blood vessels versus the interstitial space. So as the equation shows here, it's a function of the vessel hydraulic conductivity, which is just the permeability of the vessels, and then PV minus PI, again, the pressure gradient, and the term S there, which is the product of vascular surface area per unit volume. So the important part here is that pressure gradient, because like I mentioned earlier, tumors often have very leaky blood vessels, which is what allows us to use this law to model the tumors, because when we're taking MRIs, contrast agent is able to leak out, and with the intensity of those contrast agents, we're able to quantify and make heterogeneous maps of that leakiness. And that becomes an input for the model as well. Okay, so altogether, this is the model. It's a biphasic model, which is composed of a solid and fluid phase governed by the previously stated equations. Okay, so now my proposal.
Those
Oh,
dots,
sorry.
yeah, those dots are the cells.
Yes.
But,
Yes.
So but when you model it, you assume between the cell there are no gap, right? No space.
Right. Yes.
The
So
only gap is this interstitial fluids from those
right.
blood vessels. Right?
Yeah. So what we assume it's a biphasic mixture. So at every single point, there is both a solid and fluid phase at every single point.
Very good. And then
Yes.
when you replace those green dots in the center with the purple dots, that those are the tumor cells.
Yes.
And when those tumor cells become over proliferating, then you generate an internal stress from the center.
Exactly.
Right.
Yes.
And then that will influence the stress distribution there. And all the material you follow new hooking solid phase. You don't regardless of normal cell or cancer cell or the blood vessel cells, right?
Yes. Yes.
Okay.
Yeah. So in general, it covers all of the solid phase, and then those two fluid equations govern the fluid phase at every point in the mixture.
Thank you.
Yep.
Thank you. Yeah.
Yes. Well, thank you for asking questions.
Mm-hmm.
Okay, so I wanted to go back quickly to my model framework. I know I might be going ahead of time, so I'm going to speed up a little bit here, but
it's okay. Okay. I think Kevin is not joining. He has class, so we only have 3 persons, so it's okay.
Okay. Okay, so
yeah.
So some of the tissues of interest that we segment in our model are the ventricles, the tumor tissue, of course, and then the host tissue or the brain. And so the reason we segment ventricles is because they act as fluid-filled highways, which means that any fluid that's free in the brain will want to draw itself to the ventricles as they act as sinks. So again, this is relevant to that breakdown of the blood-brain barrier. The tumor sometimes comes into contact with the ventricles, which means any tumor exodus may want to shunt to the ventricles because of its high hydraulic conductivity. And again, we're able to have heterogeneous maps of this leakiness due to our DCE data, as shown on the right here. Okay. And then, actually, so my proposal is that there's another tissue of interest, which is the white matter tracts, and they are kind of aligned fiber that have anisotropic properties, which means certain properties differ along different axes. And it's actually noted that glioma cells will migrate along these white matter tracts due to their mechanical environment. And on the left here is just some images that show white matter versus gray matter. And then on the top is a diffusional tensor imaging, which again highlights the anisotropic properties of white matter. So my specific aims are to characterize the mechanical field within tumors and surrounding host tissue via improved computational methods. And by improved, I mean including more anatomy and making it more physical, which is that white matter. However, one of the issues that you might have noticed is that white matter versus gray matter is pretty hard to distinguish in the rodent brain as opposed to the human brain. So we can't see as much of that gray matter, white matter distinction in these images. However, one of the things that we can see very well is this M-looking structure called the choroid plexus. And it's actually been shown that vimentin, which is often upregulated in the tumor, is also either upregulated or migrates along that choroid plexus. And so I think that it's a good place to start if I can at least segment this tissue specifically and see how it impacts the mechanical environment by including these. And then the next aim I have is to quantify any possible differences between two glioma cell lines, which is the U251 and the 9L cell line. So the U251 is a non-immunogenic human-derived glioma, and the 9L is an immunogenic rat-derived gliosarcoma. And again, another issue that could come up here is the fact that I don't currently have any modulus values for the 9L cell line, specifically the elastic modulus, which is really important to the model. However, to mitigate this, I can conduct a parameter sweep, which just essentially means I will run the model with a range of elastic modulus and see how it matches with any literature values found.
But why here you do the cell line? Why you study cell line?
So my goal is just to see how the differences between the two cell lines.
Why you need
And
to, but you don't need to use computational method. There are many experimental methods that can help you. So
sure. Yeah,
Mhm.
I just wanted to quantify more of the stress and pressure and flow fields and the possible differences between the two cell lines and how either one could be a better match for modeling drug distribution based on those results.
So you will put a cell line in the brain?
So my goal is to use different properties for each cell line to see how that impacts the mechanical fields.
In the brain? In the brain?
Yes. So I have MR imaging and DCE data for both of these cell lines, and I'd like to see and quantify the differences in the mechanical fields.
So, okay, so you said you have those data. So other people have injected those cell line, glioma cell line into the mouse brain.
Yes, our collaborators have, yes.
Mhm.
Yeah.
Okay.
And they're really interested in seeing what the differences are between those. So I am as well.
Yeah. Okay, cool.
Okay. Yes. All right. That was it. So there's my references and
Yeah. Very good. Very good. Let's thank Isabel together. Very good. It's a very nice project and it's very unique to employ the advanced computational methods to infer the mechanics properties of the brain tumors. So in this way, they don't need to always rely on the experiment to calculate, to measure mechanical properties of the tumor. Once the modeling works, once modeling matches with the experimental results in the calibration stage, then in the future, they can just use the image taken from the clinical practice from the patients. Then you can infer the mechanical properties in the brain tumors, right? So that's actually very nice method. Good, very good. Yeah.
And let me know if anybody has questions. I know I had to talk really fast and might have not made sense. So
yeah, please ask questions, guys.
Oh, I have a question. How are you able to use MATLAB for the imaging of the brain?
Yeah, sure. So the data we use is 3D, but it's basically a series of 2D images that we have. And so one of the previous PhD students who is now a doctor, but he created a really cool MATLAB script that lets me upload 2D data, but then process it in a 3D way, if that makes sense. So I could share the MATLAB scripts if you're interested and we could talk about it more. But yeah, he just wrote a couple scripts that allows me to use 3D data in MATLAB.
Oh, that's really cool. Thank you.
I've got, I think, two questions. The first thing is I'm curious about could you recap the major like physical methods used to, I know like Laura's interested in the MATLAB script. I'm more interested in how you're actually imaging the brain because I think I didn't fully understand that.
Sure, yeah, I didn't cover that too much. It's our collaborators over at Henry Ford Hospital take control of the experimental and MR imaging. So that's all the way up in one of the M states. I forget which one, maybe Massachusetts, one of those. But essentially they'll have the tumor cell line, they like inoculate it over there. They'll inject it, let it grow, take MR to ensure that it's growing. And then after a certain point, they'll take interstitial fluid pressure measurements of the tumor and then image it at that time point as well. That's more of a timeline. I don't have the specific data at hand that covers the like the TR, T1, and T2s information, but I could get it and we could have a discussion after if you would like.
Gotcha. Okay, that's interesting. I was wondering, is there any way you could send your PowerPoint out to everyone?
Yeah.
Or I don't know if Dr. Tong, if you already have an idea for everyone sending you their PowerPoints and then making them all accessible somehow, because I'd be interested in looking back at your PowerPoint.
Sure. Yeah, I could email it if not, if anything.
Okay,
Yeah,
great. I'll
just-
put my
just-
email in the chat.
Yeah, that'd be great. And also our recording the lecture will also be available as well. Very good, very good. Any other questions?
Oh, I have a quick question. So I just a little bit curious about how you apply the Darcy's law into the modeling.
Sure. Can I ask, like, in what sense?
And so I mean then so how you use the Darcy law at a theory for your modeling.
Let me pull the slide back up.
So
Okay,
the
so
page page 9 and page 11 maybe,
sure,
or page
yeah.
12. Yeah, so
Mhm.
that you mentioned the Darcy's law, and you put
Mhm.
Darcy's law in a biophysics material theory. So
Mhm.
how you apply the Darcy law for the modeling?
Sure. So I think it's mostly relevant when you think about the source of fluid. So in the tumor, like I've mentioned a few times, there's going to be leakiness from the vessels, which means there's fluid. You know how like the conservation of mass usually equals 0 in most of our classes? In this case, it equals some source term Q, and that's governed by that Starling equation that I showed. However, the how do I say? So like where the fluid goes is driven by Darcy's law, which basically just says that it's the where it's going to go is defined by the pressure gradient. So from the region of high pressure to low pressure, and because that tumor is growing where there isn't really space for it to grow, there's going to be lots of high pressure in the tumor. So it's going to want to leave from the tumor into the surrounding regions. That's how I see Darcy's law. And then again, it's a function of that hydraulic conductivity. So the permeability of the tumor and the surrounding tissue will tell you where the fluid's going to go. Does that help?
Okay. I see. Okay, thank you.
Yeah. Let me know and I can talk more after class as well.
Okay. Oh yeah. So okay.
Okay. Yeah.
Thank you so
Good.
much.
Yeah, that's the purpose. That's the purpose. That's we have more discussions even after class. Okay, scientific discussions. Yeah. Good. Any other questions? If no other question, let's thank Isabel again, and then Trenton, you can share your screen. Trenton and Stephen, right? Chess.
Yeah.
I should call you Chess or Stephen.
I go by Chase typically. Yeah.
Okay, but why in the syllabus you also in the class list you also have a Stephen?
Yeah, my legal name and my name in Canvas on the registrar is Stephen, but I go by Chase typically.
Yes, it's fine. Good, very good, very good. So, yeah, you guys can start whenever you are ready.
All right, so our presentation is on the physical modeling of the fluid flow of aerosolized particles for therapeutic purposes. Just a quick outline. We're going to give a bit of background, provide the knowns and unknowns in the field, then move into our specific aims, the plan to put those aims together, and then any expected results and future goals that might arise from it.
All right, so just a little bit quick background on aerosols. An aerosol, by definition, is just a suspension of fine solid particles or liquid droplets in air, which can be a natural occurring like fog or dust, or even pollution. And then it can also be synthetically like made for targeted use, like sunscreen sprays, deodorant, or pharmaceuticals. And then nearly all aerosols are polydispersed with a wide range of sizes within them. And then between aerosols, those particles can range from size on a few nanometer scale to hundreds of micrometer. And this difference in size, as well as a few other things that like govern the flow, make the study of the aerosol flows pretty complex. This general dynamic equation, which kind of gives the evolution of the density of particles in the aerosol flow, is governed by the convective transport or bulk flow transport over time, but also Brownian diffusion and then the coagulation of the particles and any external force that acts on that flow. So the flow dynamics of the aerosol, I said, is very complex. It's still being researched and requires powerful computational methods to study its flow dynamics. So aerosols and their applications in pharmaceuticals, they're being increasingly used to deliver therapeutic agents by inhalation of aerosolized medicine. Typical examples of this are just like your classic inhaler, which is shown on the right, or a medical nebulizer, or even a nasal spray. And they're being used in applications to treat many respiratory diseases in patients, primarily because it has a huge advantage of delivering the medication directly to where it's needed in the respiratory system, which is effective in lowering the dosage required when compared to typical oral administration of the pill or other medicine. But one of the biggest things that's being studied and needs to be known about this aerosol is how much of the dose reaches its expected target area. You need to understand how much is deposited in the lungs typically is the targeted area so that people can accurately design the aerosol device, and create dosing regimes for these aerosols. So what's known, what's out there, there's been several studies conducted that measure the effectiveness of aerosol and how much of the dosage reaches its target area. Studies been done for decades, but there's been three primary ways to help study how much is deposited in the lungs. You in vivo using human volunteers, using imaging techniques like planar imaging or photon emission tomography. They also use in vitro physical replicas of respiratory tracts, and then just computational fluid dynamic models of the flow and the geometry. And through all these studies, there's kind of been synthesized three main components that is understood to largely affect the deposition of the aerosol. There's the particle characteristics, like the size, the density of the charge, the particles, and also the airway geometry of the patient, which can differ due to their age, their gender, or the illness afflicting the respiratory system. And then also their breathing patterns can be hugely important to deposition, the frequency of their breaths, the volume of their breaths, and then the length they're holding their breath after they're inhaling that aerosol. So the gaps we're going to highlight here are mainly highlighting some gaps of the physical model use in studying therapeutic applications of aerosols. Physical models have been effective in studying the inhalation of ambient or hazardous aerosols in the environment, but in studies that focus on the therapeutic aerosol application, there's a couple downfalls. Primarily, it underestimates the deposition, the oropharyngeal region. One study even reported as much as 60 to 70% more deposition in human volunteers in this region than predicted by their physical models. So studies have found that there's a number of factors that kind of dictate the deposition in this region that need to be accounted for, including the mouthpiece diameter of the aerosol device, the particle velocity of the aerosol, and even electrostatic effects. So some modifications that need to be made to these models to better be used in this therapeutic aerosol application is it needs to account for 100% inhalability. The models that are used in like ambient environments aren't assuming that you're inhaling the entire dosage or whatever the aerosol with some forces coming out, but in therapeutic applications, that aerosol device is typically seated in the nose or the mouth and has some large initial velocity as it comes out. There's also deposition on that aerosol device itself of the particles, which can range from 1 to 2% in inhalers to as much as 50% in medical nebulizers. And then, of course, that deposition in the oropharyngeal region needs to be accounted for, because as the model underestimates that deposition, it actually greatly overestimates the deposition in the targeted region of the lung, which needs to be more accurate for these models to be effective.
All right, so with those gaps in mind, we developed two aims. The first of which is to develop that physical model for the pathway that the aerosolized particles will take from the mouth to the lungs. And then the second aim would be to accurately mimic like the negative pressure flow conditions that are generated by both regular lungs and diseased lungs during inhalation. So just a little bit more detail about the plan for the first aim. The region that we're really focused on is just the oropharynx, the larynx, and then the trachea. So this region here that you can see in the image on the right. The major issues in those areas are the impaction, which that occurs in the oropharynx that we talked about earlier. And then the other one is sedimentation, which occurs along the length of the larynx and the trachea. And then for the actual physical model, the two kind of things that we want to replicate the most are the cartilage rings that are in the trachea, and then the ciliated epithelial cells. The cilia are really small, like within a range of 7 microns. And so that's pretty hard to replicate in a physical model, as well as the mucus that they're responsible for moving around in the trachea. And so what we want to do there is use a polyurethane tube, but try to match the roughness coefficient of the inner surface with that of like what cilia would be. And then the concern with the cartilage rings around the trachea is that it would impact flow dynamics. And so for that, we've actually seen Kevlar be used as a cartilage substitute. And we stuck with those two materials because we wanted it to be a long-lasting, robust model that could be used over and over again without any degradation. As for the mimicking of the inhalation, we want to design a contraption that can range in terms of the negative pressure that it produces. So it'd be attached to that replica of the trachea, larynx, and oropharynx complex. Negative pressures typically range from 29 to 74 millimeters mercury as a maximum. And so the upper range of what we want the device to perform at would be that 74, and then we'd want it to be able to go even lower to replicate more diseased lungs, people that can't inhale as much or can't inhale as long. And so the biggest thing that we want to vary here experimentally is just the airflow. And that's why we're focusing on the negative pressure created. The mechanism delivery, meaning like inhalers, nebulizers, things of that nature, the particle size, gas properties, those types of things we'd try to hold as constant as possible. So for instance, we might use a pressurized metered dose inhaler with a constant particle size. And that would allow us to just try and vary the negative pressure, which could mimic things such as disease progression and inhalation patterns. And so what we expect in the short term is a working model that kind of replicates what we see in terms of the therapeutic deposition in the lungs, and that would be currently reflected in experimental clinical cases. And then in the long term, we're hoping that a very accurate physical model would allow us to kind of put together a database where you can cross-reference the important aspects of the therapeutic delivery, like particle size, density, the disease progression, the type of machine that's delivering particles, everything that we mentioned previously, and kind of get an idea of how to treat patients or develop research for future drugs and therapeutics. And then these are our references, and we will take any questions.
Very good, very good. Can you guys hear me?
Yes.
Yeah, very good. Any more questions?
Oh, I have a question. So why is it like when people have aerosols, why doesn't the flow go directly into the lung? Is it because of the motion of the particles?
So there's like a few reasons. The first one is that impaction issue that we came across, and usually that's caused by the rate of release from like the inhaler or whatever it is, or the propellant that's used in there. I know one article mentioned like they use chlorofluorocarbons as a propellant, and then when they change to hyofluoroalkenes, I think the flow rate, the jet out of the inhaler was reduced, and so that allowed it to get past that oropharynx turn. And then the other thing that we're looking at is the sedimentation, which is also somewhat dictated by the flow of the particles and how fast they're going. And it actually depends on whether or not the air resistance is greater than gravity, because that'll kind of knock it out of the path that it's following and lead it to the edges of the trachea or larynx. And then the last one that we didn't really touch on was diffusion, like actual diffusion in the lungs themselves. So once it kind of starts reaching the distal areas of the lungs, it might just diffuse away now that it's lost most of its energy. It might diffuse to a different region of the lung that's just not the targeted location.
Okay, thank you.
Good. Any other questions? If no other question, let's thank Trenton and Chess together. Very good. Good. Yibo.
Okay. Can you guys see my screen?
Yes.
Okay. So, hello everyone. I want to introduce my project today, and my topic is modern diffusion using stellar automata. And this is my presentation outline. I will firstly introduce the diffusion model and stellar automata with some applications, and then go through the question part and research plan quickly. The first thing I want to talk about is diffusion, which is an important concept in both biophysics and fluid mechanics. As we learned in this class, diffusion is the net movement of anything from a region of higher concentration to a region of lower concentration. This process is driven by a gradient in Gibbs free energy or any chemical potential. Because organisms need to metabolize for life sustaining, the transportation of substance into and between different cells must occur all the time. It can be a 2D diffusion in a membrane, or 3D diffusion in nucleus or cytoplasm. For example, the transportation of sodium and potassium ions across the cell membrane is a kind of diffusion, which is called facilitated diffusion. As shown in this figure, in the resting state, there are a lot of potassium ions distributed inside the cell, while sodium ions are distributed outside the cell. As the action potential, you can see sodium ions diffusing into the cell through one ion channel, while the potassium ions diffuse out through another ion channel. For multidimensional diffusion, the best approach to find out how it works is to model the diffusion. Diffusion can be modeled by differential equations from Fick's laws. By solving the diffusion equation, the relationship between particle concentration and time or position can be obtained. As you can see in this slide, Fick's first law shows that the flux goes from regions of higher concentration to regions of low concentration with a magnitude that is proportional to the concentration gradient. But these equations might be used when we need to know the magnitude of the diffusion flux. So mostly we will use the Fick's second law to model the diffusion. In fact, Fick's second law shows that the change rate of concentration within a volume is proportional to the local curvature of the concentration gradient. There is an example of diffusion model derived from Fick's second law. This model describes the steady state oxygen diffusion in a spherical cell. In this slide, you can see the second derivative term, which is just looks kind different from the primitive one. It's because this model is built in a spherical coordinate system, and the Laplace operator should also change its form. You can see how the Laplace operator changed in this table under different coordinate system, or you can just derive it by yourself, but it's pretty complex. And also you can see there is a special term to describe the oxygen uptake kinetics, which is Vp over P plus Km. There are also many other kinds of diffusion models, like the model of oxygen diffusion from the blood vessel to intracellular organelles, and the model of nutrient diffusion in 3D tissue constructs. Okay, so the next thing I want to discuss is the cell automata. Cell automata kind of describe technique to mimic the physical system. A cell automaton consists of a regular grid of cells, which also called, and the cells which are also called lattice. Each of them is in a finite number of states. The state of this cell changes according to a set of rules that determine the new state by associating it with the current state and the state of its neighbors. And there is an example of how the cell automata works. It has found applications in many areas. In this slide, there are two applications of cell automata in biological modeling. The first one is called a excitable medium, which mimics the behavior of nervous cells, muscle cells, cardiac function, and chemical reaction. The second one is called branch automata, which simulates a form that bacteria colonies attain in a nutrient-depleted culture.
That's very interesting model. Can you explain to us this model is based on what kind of algorithm to work? So CA. It's an element, right?
In fact, mostly it depends on its special cell automata rules. For example, like this branch automata, probably it's gonna be simulated as there is a lot of nutrients surrounding one cells, and any cells will be probably will attribute it as a special growth rate, so that it can just grows like this branch form. But I'm not sure whether or not it just works like this, but it's just a hypothesis.
Yeah, can you explain what is the CA in just a few sentences? Just to tell us the key point. What is the CA?
So CA matter is just a kind of
Who developed
algorithm?
Yeah, who developed
That's
this
the
algorithm, and what kind of application people already achieved using this CA?
By using this CA, people mostly just can easily modeling any just real physical system, and
Yeah, when you explain to people any new concepts, you need to convince people first. You need to explain what is the real physical mechanism behind it, why this is useful, what kind of previous examples already show the promise of this method. And then you talk about how you use this method to solve your specific diffusion problem. Okay, so tell a story to convince people. Can you do that?
Probably not now. So
I don't understand what is CA. Go back to another previous slides.
Okay.
You are talking about, you wanted to convince us. Yeah, this one. Okay, discrete mathematical idealization of physical system. What kind of physical system? Continuous system.
I mean, most of the physics system in real life can be just simulated by
solid or fluid. Can they also work on the fluid dynamics?
Yes, I think so.
Do you have an example? Don't just say yes. Can do you have evidence? Do you have evidence the previous people's paper? I have never heard about this word before. Either maybe because I'm limitation of my knowledge, but it's also maybe because this one is not very popular. It could be multiple reasons. So you need to explain to people what it is and then convince people that this is really useful.
Okay.
Can you do that now?
Yes. Maybe later.
Later means what? Next month?
No, probably just I need to adjust my PowerPoint.
Adjust your PowerPoint. So, but right now you don't understand it.
No, actually, I can just tell you how it works. But
yeah, don't wait.
But just in the next slide.
So now this is a good chance for you. So what I have asked you is like, I'm a lay person. I do not understand this one. I don't know this. So you are the expert, and as an expert, if you want to explain these things to people, you need to tell a story. Okay, that's why I keep saying tell a story to let people believe this, and this is a very good chance. If I ask this question to you, means you have not tell a good story to the audience. If I don't understand, maybe many students, many of your classmates also don't understand. That means your presentation is not delivered very well. Can other people understand what Yibo was talking about, the CA? Do you guys understand? Is this just my problem? Do other people also understand what is the CA? Isabel, you did many simulations, right? So do you understand what is the CA?
Yeah, so this might be a little bit out of my wheelhouse just because we take a look at things from, like I said, a continuous. So I don't really go down to the cell level in my modeling. So it's pretty different from what I do.
Pretty similar. Or pretty different?
Pretty different.
Pretty different.
Yeah, we don't take a look at the cell by cell kind of
pretty different
environment. Yeah.
Okay, so but if Yibo use this new method, there must be some background there, some useful, good reasons there, right? So do you understand what Yibo was talking about? Isabel, do you understand?
Is cellular automata a simulation software?
No, it's not a similar software. It's just like an algorithm of some, but
That
it's
is
a
even better.
discrete algorithm.
If it's algorithm, that's even better. That's even more interesting. So Ivo, you need to explain it in a deeper way. Okay.
I mean, mostly it's deeper way to describe Sailor Automata is by tell a special story about the Sailor Automata rule.
Which rule?
The rule is something like a state transition function. So it can be, it can be just tells short story about that, but it's gonna be pretty, pretty complex if you want to know it deeper.
A little bit better. I think you are improving. When you keep talking, you get the story to be better and better. That's good. So you can continue. It's good. That we are learning new things. Good.
Yeah.
But make sure that when you explain, when you make the PowerPoint slides here, you should put more recent paper. Don't put the paper. It's fine to have a 1992 paper, but you should also put some very recent paper to be in parallel. That's more convincing, right? You need to tell people the cutting edge in technology, cutting edge applications, right?
Okay, I will do that.
That will help you a lot. Then this PowerPoint, this presentation will be much better. I'm trying to help you. Okay. Yeah. Okay. This is a very common mistake that sometimes you focus on some quite aged literature, but you also should not ignore some recent literature. You should add the recent literature to be in parallel. Okay, very good. Ivo, go ahead.
Okay, so after introducing the serial port, my question is, can we just utilize serial port to simulate the diffusion and use it just so a numerical solution? Because compared with setting boundary conditions in the present differential equations, it's much simpler and more direct to change the rule of Sailor Automata. So therefore,
what is Sailor?
Oh, sorry.
Can you repeat that sentence?
Oh, okay. So it's much simpler to and more direct to change the rule of Sailor Automata.
What is cellular element? Cellular element.
No, Sailor Automata. It's just say. It's just the same.
Oh, C Ultima. Okay.
Yeah.
Okay. Good.
Okay, so my hypothesis is that the change of a concentration gradient and boundary conditions and can be interpreted as a special state transition function. And also there are enough lattice to simulate an accurate numerical solution. So for the proposed research plan, the first aim is to simulate the motion of each particle because it's a discrete algorithm. Actually, there are many ways to realize it. One way to apply 3D random walk model on each particle, and the particle in our model will move along 6 main directions of the cubic lattice. And at each time, the directions of lattice are rotated by an angle randomly with equal possibility. And also the possible rotation angles are the 6th choice. And meanwhile, the particle will also move to the next lattice along the selected direction. And after all, we can summarize the particle motion and transfer it into the dynamic rules for our Sailor Automata. And also, the second way to use the solution model, the movement of particles will follow the concentration difference, and each particle will be assigned the concentration weight. and this concentration weight is going to decrease with the particle displacement. And the initial state will be set as particle cells with high concentration weight, and the final state will be all the lattice in the cell with uniform concentration weight.
Good.
So my general research plan is to solve a specific diffusion problem first. In this problem, the continuum diffusion will be discretized, and each diffusing particle will be simulated based on the C rules. Also, we can transfer the boundary conditions to special rules as a concentrate to our cellular automata. And then we will set particle cells in specified area and release the particle at the beginning of the simulation. After the simulation, a statistical analysis will be conducted, like calculating the possibility distribution of particle displacement. And we're also going to compare our results with those obtained by other approaches. And there is an example of the spherical diffusion. Okay, this is my reference page.
Good. So, Yibo, when you present those work, many questions like I asked or other people asked during the talk may already be content, the solution, the answers may be contained in the rest slides of the lecture. Okay, so then you can tell people that, not tell them I can explain it later, not say that way. You tell people that I understand your question. I have the answer in the next few slides, and I will show you when I get to there. Okay, so don't give people the misunderstanding that you will explain to them after 1 month. Don't give a misunderstanding. Every time, clarify all the things to the best level you can achieve. Don't leave any room for the confusion. Okay, you did a good job. Good. Any questions for Yibo? Any questions for Yibo? If no question, let's thank Yibo as well as all the speakers today. Good. It's a good practice. Don't be afraid to make mistakes, or or if you couldn't present clearly for the first time. That's always happen. So this is a good practice chance. So then after you practice many time, and then correct your mistakes or improve your lecture based on people's questions, then your presentation will be much better, much better shape. Okay, so will be much better. Yeah. Okay, so